Um, okay. So let's continue our course talking about whatever we were talking about last time. So we're going to talk about statistic from now on. Basically, we're going to talk a lot, maybe for next few weeks, about statistic. It's not that heavy statistics, so it will be totally fine. You can follow it easily. So yeah, we already talked about, I wanted to talk about the grading here. And another thing is about the homeworks. Now you have the basically, show you that later. The same thing, you have the files there already in your system. The home, not the homework, sorry. Oh, sorry, I forgot. About the homework 4, the deadline was Friday, but because we were not supposed to do anything that particular week, so I got just half submission, half not submission. I'm going to extend the deadline for the homework 4. Okay. Let me just do it here. I'm extending it till this Friday. Okay. I'm extending it this till Friday. So whoever did not submit the homework 4, please do so. You have the time until this Friday by midnight. It's clear? Any questions?
No.
Okay, so those that submitted is fine. Those that did not submit it, just submit it till this Friday. Any more announcement? You already have another homework. Okay. I'm going to talk about the next homework in the middle of the basically our talk. Let's continue this. So last class, 2 weeks ago, we talked about sampling. We talked about 2 types, deterministic sample and probability sample. Deterministic sample, basically, we talked that it doesn't involve any chance. If you remember when we were talking about, for example, that most solved movies in the, for example, history, you remember we could, for example, sample the code, for example, just looking at the, for example, the movies from the company Fox. So that was a deterministic sample because it doesn't involve any chance. So we are looking for particular instances from our data set. Another one is like probability sample. Okay, so you can follow my mouse. So probability sample is basically involves chance, involves chance. So before the sample drawn, you have to know the selection probability of every group of people in the population. Also, we mentioned that this is an important point. You cannot just pick some examples and call it random. You remember we were talking about the randomness, but not all individuals have to have equal chance of being selected. We mentioned that it's not necessarily a condition. And we talk about the distribution. We talk about probability distribution. We talk about empirical distribution. In probability distribution, basically, we had random quantity with various possible values. And for example, when we were talking about tossing a coin or rolling a die, and probability distribution basically was involve all possible values of the quality of the quantity and the probability of each of those values. For example, talking about talking about a die, throwing a die and seeing the probability of, for example, having 5 or 6. So you could we could do basically that with probability distribution. For example, we knew probability of each of those numbers from 1 to 6 is 1/6. So we had that probability distribution. But in some cases, the probability distribution can be worked out mathematically without ever generating or simulating the random quantity. For example, in the case of throwing a die, we can do that mathematically. We don't need necessarily to do simulation or, for example, generating some random quantity to study the probability. we could just do it mathematically, pure mathematically. But it's not always the case. It's not always we can do some measuring some probability mathematically. Remember we were talking about the probability, for example, someone clicking on some particular advertisement, or I don't know, for example, the probability of I don't know who is fan of Game of Thrones, for example. Okay, it's not those things you cannot really do mathematical equation and find out about that. You need to do basically sampling the society or sampling your data set, which in that particular example with the society, and doing the study. So another one was empirical distribution. So it was based on observation. And observation can be from repetition of experiment. For example, in this example that I mentioned about seeing, for example, who in the society prefers Game of Thrones over Lord of the Rings. In order to do that, you have a society, you can sample them, sample some people, of course, enough number, considering all those randomness, and then study them. Or you can do the same study and repeat it multiple times, and then you get your basically empirical distribution on who is fan of Game of Thrones, who is fan of Lord of the Rings, for example. So empirical distribution involve basically all observed values that we are observing from our samples. And it was basically the proportion of counts of each value that we have. And we talk about this large random sample. These are the things that we covered last time. We mentioned that if the sample size is large, then the empirical distribution of a uniform random sample resembles the distribution of the population with high probability. So let's go back to the code here. If you see, I'm running basically everything on my local host. I'm not using the server. I can use it, but I find it much more slower and problematic. You can totally do this. If you have problems connecting to the server, you can totally install the Jupyter, install all the necessary modules, and do everything localhost. That's much faster. It's much easier, actually. I mean, I recommend you to do that. But still, the server is working. You can still use the VPN and access that without any problem. So, okay, I call this necessary, basically, modules that I need. So let's define a die. Okay, so we define basically a table that has basically it's our die with our faces from 1 to 6. So if you had any question at any time that I'm talking, you can just ask me your question. Okay, you don't need basically wait for any moment. You can just unmute and ask the question. So here we are defining a table, calling it die, and it has 6 faces, right? So you remember this this one, that we could take a sample. We could take basically a random sample. So if I can take basically different samples. So each time I roll a dice, it's basically exactly look like rolling a dice. I roll a dice and I get 4. I roll a dice, I get 5. So because we want to do this multiple times, let's define, basically, we define here functions, and we did basically a histogram of the probability of each phase. Okay, so this is basically around 60 point something are the probability of each of those 1 to 6 phases. So what I do here is basically, this is the probability of exact probability, let's say like mathematical probability of each phase. But here, what I'm doing some empirical study. I'm throwing the dice 100 times, and I'm counting how many 1, 2, 3, 4, 5, 6 I have. Okay, so if I, for example, throw the die again, I get different. Each time that I throw die, I get different. So remember, we were saying if you increase the sample times, basically what you do is you're getting closer to the basically probability distribution in this case. So if I do that 1,000 times, I get much closer. If I do that 10,000 times, you can see I'm getting exactly close to what's the actual distribution is. If I throw it 100,000 times, almost pretty close to exactly the same probability that we see mathematically. So let me go back here. No, here. So let's talk about, for example, if we want to throw a die and we want at least, we're going to roll a die 4 times and we are going to calculate what's the probability of having at least 1/6. So you remember, you could do basically, this is the probability of not having 6, this one, 5/6. And we're doing it 4 times. And then we basically do that -1. So here we get the probability of throwing die, for example, 4 times without, what's the probability of getting at least 1/6? So if I do, for example, throwing it like 9 times, what's the probability of having at least 1/6 after throwing dice 9 times, or I don't know, 20 times? You can calculate it this way. You remember this equation? Everyone, you remembered it? Okay. So here, what I'm doing here, basically, I'm defining this table, and I'm throwing the die like 50 times, okay? And I'm calculating the chance of at least having 1/6 in those 50 times, and I'm putting it in a table. So I have a roll, I have a chance of at least 1/6 here, and I'm doing that basically 50 times. So you can see you have basically all the probabilities here by the how many times you're rolling your die and what's the probability of having at least 1/6. So if we scatter plot this table, okay, so you can see the probability of having at least 1/6 grows exponentially rapidly. So basically, after a few times, the probability, after like around 20 times, the probability get near 1, or like basically what it means near 100%. Not exactly 100%, but near. Here we can look at it exactly what's the probability when we are throwing dice 20 times. So it's 97%. So it's pretty high. Basically, it's almost not 100%, but pretty high. So what we did here, basically, we did it mathematically again. Okay, we use the mathematics, basically the power of mathematics, in order to calculate the probability of different basically chances that we get by throwing die multiple times. But let's do that now with basically using power of computers, using simulations, not mathematics anymore. So we basically define our die again here. We have the faces, and we taking random samples from this basically die 20 times. You remember this one? Random choice?
Yes.
Okay, so we throw it 20 times. This is our sample. This is our outcome. If I basically do that again, I get different one. Each time that I basically get a sample, I get different outcome. So let's see, for example, in the last run, like this run, how many 6 we have? We have 2 6. So basically what here we do is we do, if I, for example, should let you, if I run this, basically I get false, false, true, true, then you can do the count non-zero and count how many 6 you have there. So here we have 2. So basically I throw the dice 20 times, I have 2 6 there, okay? But I wanna do it much more, I wanna do it multiple times. So I'm not going to do it manually. I define a for loop, and I throw basically what we do here. We run this 1,000 times, and we each times we take 20%. Okay, each time we basically sample 20. We get the 20 samples. We throw the die 20 times, and we count how many 6 we have, and then we added them here. Each time we get basically a 6. Then we divide it by the number of basically trial, 100%, 1,000 times that we did. So you can see it's get pretty close to what we did mathematically here. This is what we calculated using mathematics. This is what we are calculating using the simulation, using the basically empirical study, not math anymore. So if I increase this, it should get much closer to the basically to the actual value. Oh, that was too much. So you can see if I throw it like 100,000 times, I do that 100,000 times, I get pretty much the same, 97.3%. Is it clear what we're doing here? Okay.
Yeah, it's clear.
Yes.
Perfect.
Yes.
So let's go back to our slide. So let's talk about statistic. I'm not running this like a slideshow because I don't want to switch back and forth. So talking about the statistic, we have basically, we already talked about probability, statistic, sampling. Those are basically the fundamental topics or fundamental areas when you're talking about statistics. Statistic basically generally used to be doing some study, for example, from the society, from the data that we are going to basically, we are interested in. We do some study on that, and we get we already talked about probability, how we calculating it. That basically probability is where we're doing, for example, in that throwing die case, we throw a die and we calculate the probability of having, for example, we're throwing and we're studying probability of one event. And in the statistic, we are doing the same, but in a different way, right? And basically, and the sampling is the basically, how can I say? It's related to both area, both basically topics, probability and statistic. Let's talk about the estimations. And basically, what we're doing when we're talking about statistic is statistical interference is the main thing that we do. It's basically making conclusion based on data in random samples. Usually what we, not always everything is straightforward, like throwing a die. Usually whatever we're studying, we're dealing with big data that are not very easily to do mathematical study on them. So basically we get random samples from that big data that we have, or from, for example, society that we want to study, or no matter what is it. And we get a random sample, then we try to make some conclusion based on those random samples. For example, we use the data to guess the worth of an unknown number. This unknown number should be fixed. It cannot vary after each experiment that we do. Otherwise, basically, we are not going to drive any concrete conclusions. And then we create an estimate of the unknown quantity that we studied, or unknown number that we studied. And this estimate depends on the random samples that we take from our data set. So let's talk about this terminology. The parameter is a number associated with the population. And a statistic is the number calculated from the samples that we get from that population. So a statistic can be used as an estimate of a parameters. let's go back to the code. It becomes everything easier here. Okay, let's do the same thing. Okay, rolling dice. So we are defining functions. Okay, then we having this for loops that runs as many numbers as we put on the trial here. So what I want you to just check this code, okay, and tell me how many times I'm running that. How many times I'm rolling a die here? You can unmute, you can think loud, it's fine.
In that case,
1,000.
we need
1,000.
200.
200,000?
200,000.
Yes.
Yeah.
Confirm?
Isn't it 4 million?
Who said 4 million?
David Garcia.
Any other guess? Yeah, just tell me some numbers. So
I
we
think
have
it's
200,000, we have 4 million,
I think it's 4 million.
4 million. Any other guess?
200,000.
200,000. So basically what we're doing here, we're calling this function 1,000 times, right? Here, just in this line, then we are basically running this loop 200,000 times. 200 times we're running this, 200 times we are calling this function, which is 1,000 times we're calling that function. So here is just we have 200,000, right? Then we have a 20 here. What about this?
Yes, because you make 20 choices, like 20 different choices of the result of the dice.
Exactly. So basically, it's all these 20, 200, and 1,000 here, right? So it's 4 million times. So basically, I'm running here. I'm throwing die 4 million times, and I'm estimating the probability of having at least 1/6. So if I, sorry, if I run it again. If I bar chart that, you can see the distribution, okay? The distribution of all these probabilities that we are trying is something like this. So you can see in the center, basically what we had, the actual value when we calculated mathematically was this, right? 0.973, basically 97.3%. So what we see here, most of the basically our sample are around the same values. So if we do the other way around, you can see that we get pretty good estimates on our data. Is it clear?
Yes.
Yes.
Okay. So let's talk about another example. Where's the slide? Okay. There was this story in World War II. Allied forces, they wanted to know how many basically fighter airplanes German force has. So they needed to know in order to basically have some strategy for fighting against those airplanes or for fighting against Germany. So they come up with this idea that they can check basically the, how to say, the serial number on the airplanes, okay, and try to guess based on those serial numbers how many airplanes Germany have during World War II. So basically, they were observing these serial number that they were on the airplane, and they try to calculate how many basically airplane they have. So any guess, is it a real story or it's a fictional? Did I just made it up or it's a real things?
I think it's real.
You think it's real? Who thinks it's real?
Yes, it's real.
I think it could be real.
Victor Eduardo is not optimist about it, any of this. Okay, we'll talk about it. Let's define some assumption. So imagine this is the story. We have a plane that have serial numbers from 1 to n. We don't know n. We don't know exactly how many they have, but we know they put the serial numbers like this from 1 to the maximum, the number that they have. So what we would like is to estimate n, the maximum number, or how many airplane they have based on the serial number of the planes that we see. So we basically observe the flying airplanes and we try to estimate how many airplanes they have. So the main assumption is the serial number of the planes that we see are a uniform random samples drawn with replacement from 1 to n. This is the assumption that we put. This is important to set this assumption before basically continuing. So if you saw these serial numbers, what would be your estimate of n?
The largest one.
How many?
The largest one.
Yeah, I put here the.
But I mean,
Yeah.
it's not because that. It's because it's serial. No, it doesn't.
It's supposed to be like this, you know. I'm supposed to click and you don't see, but I'm being lazy. I'm not doing that. I'm going to do from now. So one idea is the maximum, the largest number, right? Any other idea you have? Any other?
Take twice the average
The average, you add them up and take the average?
and twice the average.
Okay, twice the average. Okay.
Yes.
Twice the average. Okay, so let's see. Okay, we're going to talk about both the largest one, the largest number that we see, and the average that Carol mentioned. So I'm going to do this now. So what we want to know, okay, let's say we saw that biggest number, like 291 in that case. So we want to know how likely it is, basically, that estimation that we have would be close to the actual number that they have. And we want to know how close is our estimation to their real value. So we have two options. Option one is we could try to calculate their probabilities and draw a probability histogram. Or we could simulate and draw an empirical histogram. So the first one is not that maybe easy to do. So we can basically, we could simulate and draw an empirical histogram, because as I mentioned, not everything you can calculate the basically probability easily. So let's go back to the code. So let's consider this. Let's consider the actual number n is 300, but we don't know that. So basically, this is a table of our serial number from 1 to 300. So what we can do here is we can sample 30 from this table, which is serial number. This is the table name. So what I'm doing, I'm sampling 30. Then I'm getting the maximum value from my samples. So each time I sample, so you can see, for example, the first sample I took, the 299 is the maximum number. It's pretty close to 300. So it's a very good estimate. It's a very good estimation. So if I run it again, 294, remember I'm taking 30 samples, okay, per run. 292, 298, 294, 298, 287, it's get a little bit off now, 293. So you see each time we're running, we're getting not that great, but pretty close actually. But let's do basically, let's calculate that several times. We don't want to run it and count these things and then take an average or do something like that. So what we can do is define our sample size. I'm defining like repetition, how many times I want to repeat this sampling things. I want to repeat here 1,000 times. I define these loops that are going to run 1,000 times for my repetition. So then we're going to sample from our sample serial number one. And we're going to do sample size, which is 30. And then we're going to get the max and put it in this max serial number table. Is it clear what we're doing here? So, okay, we calculate basically what we did. We take the sample 30 times. Maybe another day we went out, we looked for the airplane, we take another 30 samples, another day we take another 30 samples, and we put all those information in this table. So you can see, for example, here we have 300, like continuous, it's interesting. So let's basically do the histogram. This is the histogram from the max, basically from this table. I define the bins like this. Each step is 10. So you can see, it can be easier. Is it visible, everything?
Yes.
Okay, so we did that histogram. You can see mainly we are close to 300. So, but it's not all 300. Remember, this is each step is 10, so it's basically from 290 to 300. So we didn't estimate it exactly the number, but we are pretty close to 300. So let's go back to slides. So we see the largest serial number observed is likely to be close to n. But it is also likely to underestimate n because actually what we're taking, if we take the average, mainly we are getting somewhere around 290, 290 maybe, okay? We are falling around here, not exactly on 3. So we are likely to underestimate basically the n. So another idea for an estimate can be average of the serial number observed, okay? And then we take the basically 2 times of the average, as Carol mentioned. So let's see how is that estimate going to help us. So basically what we're doing here, we are taking exactly the same code, okay? We are adding now average here. We are getting the mean, and we are multiplying it by 2, okay? So this is the only line that changed. So if we run this, this is our table, and this is the first time that we basically did the same thing, we did the maximum. And this is the basically another one that is 2 times average. So if we do the histogram here, you can see these results. So what you can tell me about this? Anyone, any idea, any comments? Carol, you mentioned you were recommending same thing. Do you have any comments on this? Which one is better?
Well, I think that twice the average is better. We can see the distribution, like the average of the at the middle of the distribution is 300.
True. Yeah, perfect. As he mentioned, the middle of distribution is 300, so you can see we have a slightly better distribution here. So we are not really underestimating because the middle of distribution falls on 300. So we have here we are not really underestimating, but what we see here is let me do something because I have a question here. I don't want to use it to see that. Okay, so what we did here, the first time we did the maximum number, and we estimate the number of airplane by considering the maximum number. And another one is we get the average and we multiple 2, and we see basically the middle of the basically distribution falls under around 300. So it's pretty good actually. So let's do another study. Let me see what we're doing. Okay. This one. Okay, imagine I'm taking a sample of my N that I've just removed here. Okay, so this is the sample, this is the 30 sample of my N that we don't know what is it. You can see the sample numbers. So can you tell me what is basically the number of N? Okay, maybe I run this to, it might help you. This is the average, this is the max.
A 1,000?
1,000? Any other guess?
Maybe 950.
Brian saying 950. Any other guess? Now give me another number. Any other guess? Yes, tell me. Give me a number. I mean, you can see the maximum. You can see average. We already talked about different distributions. You can guess something based on that.
600.
What?
940.
940. Okay. The actual number was 1020. I mean, it's fine. You don't know that. Okay. It's basically this 1020 is the number of character Z's in all Shakespeare's 37 plays that he wrote. We had just 1020 Z. So anyway, it's a data. So we observed that this is the average, this is the max. So let's do the same study using this data. So we run it again 1,000 times. So basically it's the same thing with different data set. Now remember our N is 1020, okay? So this is the max one of all these 1,000 samples. This is the average. If we do the histogram, you see again the more or less the same results. So mainly when we're considering the max, mainly we are falling close to that, okay? Majority are close, but not exactly. We tend to basically a little bit underestimate. But when we are doing the 2-time average, the center is like falling in 1020 almost. Okay, let me go back, skip this. That's a question for you later. So when we talk about that estimation, we need to consider bias and variance. These are the two important basically things when we're talking about estimating something. Bias estimate is on average across all possible samples. The estimate is either too high or too low. So you could see, for example, in that when we're considering the max estimate, it would be, of course, the best one would be the equal, and the other one would be basically lower than our real value. So bias creates a systematic errors in one direction. Either it goes too low, or it goes too high. And a good estimate, of course, should have a low bias. It's a very logical thing. Another one is variability. Variability is the degree to which the value of an estimate varies from one sample to another. If we go, where was it? Here. So you can see this one has basically high variability, right? The 2 times average has high variability. You can see it goes all the way from here, 8 to 1,000, like 300. So the variability is very high, but it's not biased because the center of this 2 time average falls around 1020. But in the other hand, when we're considering the max, the variability is much lower. You can see variability is not that high. But it's very much biased, right? Because it can underestimate the number of, for example, our n. Is it clear?
Can you repeat, please, the bias and the variability?
Okay. Talking about this example, okay, let me finish this, then we come back to the example. So basically, variability is the degree to which the value of an estimate varies from one sample to another samples. So we are taking all these samples. In that example, we are taking 1,000 samples. So variability is how much it varies. Okay, let's say it's minimum with the maximum. What is this gap between, in that example, between mean and max? So high variability makes it hard to estimate accurately. And of course, the good estimate typically should have low variability equal with low bias. Going back to this example, for example, you can see 2 times average is not biased because the center falls around 10,020, but maybe here is more clear. Talking about this one, the center of it falls around 300, so it's not biased because this is basically a normal distribution. I'm getting some comments here. Okay. So as you can see, when we're considering 2 times average, the center falls around 300, like almost exactly. So it's not biased, but it varies a lot more than the other one. You can see the blue one varies from here to here. These are the values of the samples that we get. So here, considering the max, variability is not much, but it is biased because it's trying to underestimate our n. But 2 times average, variability is high, but it is not biased. Is it clear?
Yes.
I have a question.
Yes.
Why does the bias affect the estimate? I mean, I understand the variability, but why does the bias affect it?
I mean, for example, talking about this max number, you see, for example, these are the value that we are studying. Okay, if you want to look at the table, these are the max that we get it. So you can see in majority of the parts we are underestimating the actual value. Okay, so our estimation, this is my estimate. Okay, I get my 30 sample, I get the max, I see it's 283, so I say, okay, the Germans has 283 airplane, but actually they have 300, so I'm underestimating it. So my estimate is biased. right?
Okay. Yeah.
But in the other case, you're considering, because this is a normal distribution, so you're considering the center of the distribution is, it falls under 300. So the bias is, you can say almost, it doesn't have bias. It's not biased. Let's say almost. So it's the same case here. Is it clear?
Yes.
Okay. Okay, let me skip this. So that's what I already talked about. So basically, we said already the max has low variability. As you could see, like here, the variability is much lower, but it is biased. Okay, oops. But it is biased. And 2 times average has little bias, but it is highly variable. As you can see from the figure, it is very much variable, but the bias is not that much. So there's a trade-off basically. Okay, we cannot have both at the same time. So there's a trade-off between between the bias and the variance of samples that we have. So let's go back to the code. So for variability, for example, you remember this is my estimate. Let me. Oh, this is my estimate. This was our estimates, okay? Estimate table that we calculated about. So here we can basically calculate the variability by getting basically this column 0. Okay, and minus, I'm getting absolute value of this value minus the actual n value. Okay, I'm getting the mean of it. So basically this is my variability. If I calculate the same thing for the second column, you can see the second column, the variability is much higher. What is this? Is it clear? So you can see when we're talking about getting the max as our estimate, the variability is much lower than when we are talking about the average. In the average, the variability is much higher than getting the basically max. So it's the same thing basically. I'm just what I'm doing here. Okay, this is extra. So for bias, we can do the same thing. We can calculate the same thing for both for this value and for getting the max and getting 2 times average. So here, this is the basically we have our n, we get it minus our estimates, and we get mean of it. So you can see this is the bias of considering the max, and this is the bias of considering 2 times average. Is it clear? So basically, we are getting we know the actual n. We dividing it by the estimate that we had. In this case, the column 1 was 2 times average, and then we get the mean of it. So you can see the bias of the 2 times average is much lower than bias of when we're considering the max. Are we clear? Any questions so far? So that's why in that basically example, I mentioned that basically considering these two, the max has low variability as we saw in the number 2, but it is biased. 2 times average has little bias, almost near 0, but it is highly variable. And so this is a trade-off between these two when we are playing around with it. But this was this was the idea of getting the max and calculating the 2 times average. But is there any other options? Any idea or any other method we can get a better results? Any idea? Anyone want to share? Say something, guys. Any idea?
Combination of both?
Combination of both. Like
Maybe.
how?
I mean, maybe we can estimate with the results with the center of the average per two and the max in the other hand. Maybe.
Maybe. Okay. True. That's maybe give us a better estimates, right? Comparing to what we did here. So why you don't try for yourself? I already uploaded this file. It's Jupyter. Where is that file? If you go to the, okay, so what I want you to do now, I want you to turn on your systems, sign into your Jupyter account. Guys, I appreciate if you turn on your camera. What I put there, lecture 07. If you go to the note, you see this one, clever estimate. If you start running it, please let me know.
So do we have to run the clever estimate or the COVID-19?
No, this one, not COVID-19, this one. It's lecture, if I'm not mistaken, lecture 07, clever estimate, something like this, the name. Right? You got it?
Let me find it.
Do we create a copy or can we use?
Yeah. I don't think you can use the same. Just copy it in your note, in the note folders. So
Is
basically,
that clever estimate, right?
yes.
The one that says Lex 07 clever estimate.
Pardon?
Is it in the notes folder in the TC?
Yes. It's like 07 clever estimate.
Okay.
So if anyone didn't get it yet, raise your hand. Okay. Because what I want to do is I want to divide you to the groups of 3 maybe. Okay. Then I want you to basically come up with a better results. So how you can consider you get the better result is you want a low variance, okay? You want a very low variance, and of course you don't want your estimate to be biased. Is it clear?
Yes, I think.
Okay, so I'm going to stop sharing my screen. So I'm going to pause the basically recording because I want to divide you to different groups. I'm pausing recording.
Hi.
I cannot open my server.
It's okay. That's why you're 3 together, so you can just share one of the screen and then brainstorm on that particular, basically,
Okay.
notebook.
Yes, because I can. What?
Yeah, I mean, one of you that has already access, you can share like this that you're doing, and others, they can
Okay.
just comment on that. So try to like, think together, work together, bring ideas.
Idea.
Yeah, but
So
it's
I mean, think together and like brainstorm and see what you can do. So the idea is here, just don't change the sample size, okay? The sample size that I put up, 30. If you go up, you can see that sample size 30. Because, for example, our n is 1020. If you put that sample size 1000, then of course you're going to get the exact number, right?
yes.
So don't play with that, but any other solution you come up with is fine. And I put some idea here, like NP average, NP median. Maybe you want to play with median, which is different with average. And mean, max, you have all those things to give you idea what you can do with them. Okay?
The
I have a
idea is
question.
okay.
Yes. Yes.
No, so the idea is to change the sample size and see what is the behavior.
No, the idea is to come up with a better estimate. You remember we
Okay.
talked already about two
Okay.
different methods. For example, this is my samples. This is my sample size. You can see here, these numbers are the samples. So one time I did with max, I considered the max. One time I considered 2 times average. Maybe you can come up with a better idea. Okay, I don't know, for example, considering 2 times median can be an idea to see if you get better result or not.
Okay.
Okay, yeah, just play around with it and see how it goes. I join you later.
I think. Okay.
Okay.
Hi, Marty.
Hi, how is it going here?
We're a little bit confused.
What's the problem?
Yeah, so basically you want us to reduce the variance, I believe, right?
Okay. The idea is if you go up in the things, for example, I take the 30. Okay, here I take the 30 samples. Okay. So these are my numbers. Okay, so the idea is not changing the sample size, because if you put the sample size like 1000, of course you're going to get very close estimate to the actual value, right? So don't change the sample size. So for example, what we did in my example, we used 2 different methods. We considered the max number. Okay. Another thing we did, we considered NP average, the average number, right?
Yeah.
And we multiply it with 2. So you can come up with another idea here. I don't know, for example, it's not a great idea, but for example, you may want to say, okay, I did 2 times average. What if I do 2 times median? What result I get? Do I get a better result? Do I get a worse result? Or what other methods I can come up with? You know, what other, I don't know, what other way I can have a better estimate with a low variance, a low bias.
Okay.
I said, for example, 2 times median is an idea. I don't think going to work great, but you can try it. Or you can play around with max, mean, I don't know, or come up with your own brilliant idea.
Yeah. Okay. So basically the medium, it's not gonna work that well.
You can try. You give it a try. I mean, you never know. You can try.
Yeah. Could you try it, Eduardo? Yeah, right there. In the maxes, no, sorry, in the average, you could put where you have doubles, 2 times NP average. Can you change it to NP?
What I would do if I were you, I wouldn't I would keep this. I would add another line, so you could compare them and see which one is working better.
Okay.
So for example, you have max, you have 2 times average, you have 2 times median, you know.
Okay.
So
Yeah.
you can see how it's good. Then you can compare them together, of course.
Okay.
Okay.
Okay,
So-
I'll check. Yeah.
Okay. So in the doubles, right below it, could you
Okay.
add this, an array?
Ujú. Le pongo.
I check you later.
Right there. Yeah. Medians.
Entonces habría que repetirlo más veces a ver que si nos da un mejor resultado en promedio.
Bueno, es que
Es
la media siempre va a ser la misma. O sea, es así como ya tenemos los datos de observation, siempre va a ser la misma. Y lo que hacía el profe era que agarraba una muestra nada más.
Por eso.
Okay, guys, any questions, any doubt? I'm here to help.
We are trying to figure out what kind of logic to use to solve. Yes.
So the thing is just
we were thinking of.
Okay.
Yes.
Yeah, I'm listening.
We were thinking of taking the array for the samples we took to sort it so that the samples are in order. Take the middle sample and take double the value of that.
So in order to get the median, you don't need to sort them. If you go up, I already show you the median of the samples you get.
Okay.
So for getting median, you don't need to sort because that's how it works. You get the median of your sample. I mean, you can do it, but it's like a little bit extra work.
Yes, we were seeing that just now.
Yeah, but it's the same. It's going to work the same. So what? The idea is don't increase the sample size because, for example, the n is 1020. If you put sample size 10,000, of course you're going to get that exact number. So don't change the sample size. And also, if I were you, I wouldn't change this table max and 2 times average. If you want to play around with this, add another columns. Sorry, add another row here, like another column with your, for example, 2 times median. So you can compare all 3 at the same time to see if yours is performing better or not. Okay?
Okay.
Okay, perfect. So I'll check you later again.
Okay.
Thank you very much.
Okay, how is it going here?
Good.
I don't see anyone sharing any screen. So how are you brainstorming then?
We came up with something at the beginning of the the 20 minutes. So yes.
Okay.
House idea.
Okay. Yeah, can you share me again? Let me see. What you did there? You got the max plus min.
Yes.
Okay. Whose idea was that?
Carol's.
Okay. So you may try other things. You can add other basic solution and see if you can get a better result. I mean, you're already getting better result because your variance is lower, of course, and your bias is almost 0. So that's look like a good job actually. So yeah, you're doing good. I'll check with you later.
Okay.
Thanks.
Un maths entre dos.
Okay, guys, how's it going?
You don't know.
What happened to the sound? Why it's too off?
We're just.
It's an offset. We made it, but it's only a slightly.
I mean, it shows like this. We thought about just adding the max and the average.
So what you did there?
The average, the W average plus the maths divided by 2.
Yes. We just got an average, a simple average of those two.
Okay, so you already getting a better how to say? Yeah, I can see you have a lower variance comparing to 2 times average. You can see the variance is lower, and I think bias should be close to 0 too. So it's a better result. You already have the, but you may come up with other solutions too. I mean,
Yes,
I
that's what
tried
we're
to
trying
make
to.
with this by not by this would be made a graphic around here. So it's worse.
yeah. So try other solutions. Okay, guys, I'll check you later. I see what's happening other places.
Okay.
But good job.
Thanks.
What's happening here?
Average observation. Observation.
What you trying to do?
I got it.
What's the idea?
¿Me pasan el control?
Sí.
Aquí. ¿Les gusta?
Está mejor, ya.
Está mejor. Lo único que hice, what I did was I just took it was just the average of the two methods, of the two previous methods.
Uh-huh. So basically you add them up, then you divide it by 2?
Yep, that was it.
Yeah, I mean, it would be good if you keep the other row so you could compare them.
Ah, yeah.
Now it's gone, so.
Well.
You can have the table with 3.
Just a new array and yeah.
So that would be nice to see all 3 at the same time. To see which one.
MP append x equals MP append max. No, x.
X. X. That's it.
You are bending to doubles in the X declaration. Yeah.
Where?
X equal MP dot append doubles.
Doubles.
Isn't that X?
X.
Yeah.
It's X. That's it.
Looks better.
Yeah, you're already having the lower
variance.
Yeah, lower variance. But what about the bias?
It is not. It is slightly biased towards the max value.
Yeah.
Yeah, you think you know what you can do? You can, I mean, I show you the comments here. I can send you here. Oh, how can I send you text chat? Can you see the chat?
Yeah, I can.
Bias and minus estimates.
So basically, you put the column number that you want to compare. So now you have 3, so you can compare all 3 at the same time. I mean, put column 0 and see the bias for max, bias for 2 times average, bias for your average.
Okay.
Okay, so there it is, and n estimates
0, 1, 2.
Just and do we have an n?
Yeah, n is defined.
Yeah, we have an n. Yeah, of course. We have, just the average bias of the two methods. Almost.
That's right.
Teacher, how effective is it to use numpy.bar to calculate the variance?
Pardon?
There's a function in NumPy which is called numpy.bar to calculate the variance of an array. Is it effective in this case, or it doesn't work?
I'm not sure. You can give it a try.
We can try it.
Yeah.
¿Quieres poner tu pantalla?
No, aguanta. Ahí está la documentación. Según yo es nada más
Okay, guys, I'll check
darle el
with you
array.
later. I visit other group.
A ver.
NumPy.bar.
Es numpy.bar y adentro.
So, how's it going?
We were trying to do something like maybe with the standard deviation, but we have this now.
So it's not a good result actually.
No.
Yeah. Yeah, you can try to come up with other solutions.
Yes, we're trying to get something else.
Okay.
Do you have any tip, any advice?
I already saw some solution on other groups I can share with you. It's like, for example, in another group, they said, okay, we have the max, we have 3 times average. What if we add them and then divided it by 2? That was one of the solutions. Or another solution they came up with was, what if we get max number with the mean number? Okay. We get the max minus mean multiple 2.
Okay.
That was another idea. So you can try either of these and see if you get a better result.
Okay, thank you.
Okay, I'll check with you later. How's it going, guys? What's happening?
We're struggling.
Struggling.
Yeah, we've tried different
solutions.
Yeah, but they always give us weird graphs, so we come back to the original.
So instead of taking the average, we try to the median or the multiply by mean, but the graphs are kind of weird.
So it's weird because maybe the result is weird because the result is not accurate. So what I would do, I wouldn't change max and 2 times average. I wouldn't change this table. You can append another column here, so you can see your solution comparing with these 2 solutions at the same time and see how it works. You got my point?
Okay.
So, for example, I saw already some solution in other groups. They said, okay, we have this max column. Why your max is so low? That's a mean. Or probably you changed something here.
Here we.
Yes.
Yeah. Anyway, they said, for example, we had a max. Now we had a mean. We had max. We had 2 times average. So what if we add max 2 times average, and then we divide it by 2? That was an idea. You can try it. Or another idea was getting the max minus mean multiple 2. That was another idea. So you can try one of these solutions and see if you get better results.
Okay.
max minus mean.
So I'll check with you later, okay?
Okay.
Ajá.
Sí, sí, algo mando. Déjame.
Okay, what's happening?
Hello, teacher.
We combined the function with maxes and doubles, and
We got a nice looking
have
graph.
this.
So it's a bit mislabeled because it's no longer the median. Now it's
Result. So
a
what is
combination
it
of.
exactly? You get the
We take the array of the samples and we take the value of the biggest sample.
Max plus 2 times average observation.
And of the sample.
Yeah, your voice was cutting off. But what I can see from this code is like you get the max, you add that with the 2 times average, and then you divide it by 2.
Yes.
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 You average these other two columns. Yeah, of course you are getting better result. You're getting lower variance, as you can see. It has lower variance comparing to the yellow one.
And a comparable bias.
I assume it's the bias should be close to 0. But
yes,
yeah, that's a good job. Okay, let me. But you may try other solutions too, if you want.
We tried with the media, but we have like this. We tried mp.median from
good.
observation.
But we were getting a very high variance.
Yes, we don't have very good results.
Yeah, that's awful.
As you can see, the variance is a lot bigger.
True. But yeah, the other solution is much better.
Okay.
But there are other solutions too.
We don't know them.
So I send you a message, so you can calculate the variance.
We can't see it here.
In your chat.
I can't see it in the chat. Like I saw you sent it, but like it's not in the chat.
Yes, it's not in the chat.
No.
No.
You
It's only a
send
message.
like as a message.
It looks only like a message.
But what about now?
No, it doesn't appear.
Okay. Let me. What if I send you here?
You see, I just sent a hello, teacher. Can you see it?
Yeah. So you can use this to calculate bias.
Okay.
You can use that column number is the column number that you want. Okay, so you can do that for all the 3 columns and see which one getting better results. I mean, just by looking at it, it's too obvious that yours has better, lower variance, which is better. But about bias, maybe you better put it like what you're doing. So that column number you can do for column 0, column 1, and column 2.
Column 2. That's our.
So compare it now with the column 1.
Okay.
Just put it under so you can see both at the same time.
Mhm. Column 0 or 1.
Or 1 or 0. I would compare with 1 because with 0 it's obvious.
Okay, 1. Oy.
Shift enter.
Yeah. Okay.
Okay. Yeah, it has lower bias. No, yours has higher bias. Oh, you can see
Yes.
yours is column 2. Yours showing higher bias.
Higher variance.
Mhm. This is the.
It's not very good.
It's the variance is better as obviously, but the bias is not that good.
Okay.
But it's good. You can maybe come up with another solutions. I'll check other groups. I'll check with you later.
Okay.
Okay.
Es decir,
How's it going here?
we are thinking about the solutions that you gave us. So we were thinking what does those mean?
So here that you put max multiple 2 divided by double, you could put that another line under double if I annotate. For example, why don't you put another line here and do your calculation, put some name for it, and just put it here on this table, so it would be look like more clear, so you know what you're doing. Yeah, for example, make an array there.
And we can have the puede ser la mediana, ¿no?
What's happening here? No, there's something wrong with the code. If you go up.
The same number of rows as table.
No, you go up. So why you what is this new here? Ah, you're appending to the okay. That's appending. No access. You cannot do. I don't think you can do this here. If you want to use this, you can use this.
Yes. Oh, double over double.
Yes.
I cannot use this one. Yes, no. Well, I mean, it was
Okay, guys, I'll check with you later.
wrong anyway.
Let's see what's happening.
Por si llega Magdi. Hi, Magdi.
Hi, how's it going?
We're going there. We were showing. We were trying different methods.
Can you share what you did?
Yeah. So we try even more, but but we were like taking them out and seeing each one of them. As you can see, we even put calc to see if we were doing something. Yeah. So.
So which one is the best you got?
Well, right here on this last one, the one with the calc was the average of the max and the mean. So yeah, the max minus the mean. So we basically did try to do this to see if we were getting closer. I think we kind of did get closer. Yeah, with that one.
Yeah. No, but what I see, I mean, true multiple median is awful.
Yeah.
True multiple average is what we did. Calc isn't that great because
Yeah, it's going way up.
yeah, the bias is awful.
Yeah.
Apparently. Yeah.
Yeah. We were trying different methods. We try a lot. We even tried one that. Yeah. No, but the other ones were really. Oh, we have to add it to the table.
So.
But the other ones were really, really, really bad.
Yeah, those are so off.
Yeah, those are way up. So we were like, no.
Okay, so I think I'm gonna call it off for everyone to come back to the main room.
Yeah.
It's been, I think, almost 50 minutes. Okay.
What happened?
Okay, guys, you back to the main session. So I saw some interesting solutions there. Okay. Where is some people are disappeared. Anyone wants to? Carol Jose, where were you? Which group you were?
Hi. With Sebastian.
Who was doing the code? Can you share your screen with everyone?
Yes.
I mean, in the screen that you were doing the code. Okay.
Okay. So what
can
I
you
did
talk
is
about
to.
your solution?
Yes, I just took the mean value and I added it to the max value. So this is the solution we had. I mean, it is max plus mean, and we can see that the distribution is, well, it is close. Actually, we had better results here. It's close to 1020, and the variance is, well, we can see that it actually, the distribution is closer to, I don't know how to tell it, the
variance is, yeah.
Yeah. The variance,
yeah, true. The variance is very, very low. And the bias is almost near zero, yeah. Perfect. So there was another solution, one of, I don't remember now, again, which group was that? They add max plus 2 times average. Who was that? There were 2, 3 groups doing that. Can you share your screen? Share the code?
We combined the max method and the observation method. We sum that and divide it by 2, and we have the result.
Okay. So again, yeah, as I can see, comparing to the 2 times average, you have a lower variance. but I'm not sure about the bias.
Yes, we thought that it was better, but in the reality, our bias is more than the bias of the second.
Average. True,
and,
true.
And the variability is even worse than the first column.
Yeah. The variability of considering the max, the variability is very low, but the bias is awful, so it's not a really good estimate. The baseline was basically 2 times average, though the variability was high, but the bias was low. So though it's a trade-off, but I consider 2 times average better. But the one that Carol Hauser was showing has lower variance and very lower bias. So that was basically comparing to all the solutions, that was the best. Okay, thank you.
It was best.
Thank you. You can. Okay, so basically what I had here, if I share with you my screen, screen 2 was the same solution. I mean, I skip it like this one. Yeah, basically adding the max and min, and then doing that, I considered the best, the same thing that we saw. Okay, so let's continue with this topic. Okay. So let's continue with this topic. Before I go, it's I don't know the case in Mexico. How is basically the court system here? Do you have a jury system? Anyone has any idea about the court system in Mexico?
No clue.
It's like the system, at least in the United States, is you have a jury panel that are selected from the people, like normal people in the society. So you have eligible jurors in a county, for example. Then you have a list of eligible residents. From there, they pick a jury panel, and those jury going to help basically the judge in order to decide on a court, on a trial. I skipped this detail, it doesn't matter, it's basically in the US Constitution. So there was this case of Robert Swain from Alabama. In 1965, Supreme Court case about the jury selection was basically very controversial in this case. In that city in Talladega, Alabama, 26% of residents were Black. Okay. But so what do you expect among the 100 people that are part of the jury? You expect to see 26 people. But in his jury panel, there were 8 out of 100 were Black. Robert Swain was a Black guy that accused of raping a white woman, and it was basically had a death sentence. Okay, capital sentence. So in his jury panel, there were 8 out of 100 were Black people. So they thought it's not a normal case. They take it to the basically Supreme Court, and at the end, Supreme Court ruled that the overall percentage disparity has been small and reflect no studied attempt to include or exclude a specified number of Black men. That was a Supreme Court rule. So basically, at the end, even those 8 people that they were in his court, they were kicked out by the prosecution through this. There was this rule that they can say, okay, these people are biased, so they cannot be part of jury. So at the end, his jury was 100 white, not 100 white, but 100 non-Black people. So what we're going to study now, we're going to see, is the actual jury panel is likely? Is it likely you get randomly selected from that county 100 people where 26% of the population are black, and at the end you turn out just having 8 out of 100 black. What do you think? How likely is that? Is it possible? It's not possible. It's very unlikely. Any idea?
Yeah, it's possible, but it's not that likely.
It's possible, but it's not that likely. Okay, let's do that. Let's study the case. So basically, what we're doing here, we're defining this table. We have ethnicity, black, and other. So eligible are 26% black, 74% others. The same the fact about that city in Alabama. But in the panel, they were just 8% out of 92. 8% out of 100 were black. So basically 8% were black, 92 were others. So basically what we want to do is we're going to start with distribution of eligible jurors and the actual panel. Then we're going to draw panels at random from eligible jurors. So we're going to do some random selection from these people. And we're going to see if actual panel is likely. Then we're going to see if this random selection, by this random selection, anyhow we can get 8 out of 10, out of 100. Okay, so if we basically bar chart that, you can see this is the blue one is the eligible, the yellow one is panel. Just looking at this, you feel it's a little bit unfair. Okay, but just looking at this, we cannot conclude. We have to do the study. We're going to do the empirical study. We already talked about variation, right? That, for example, considering max, variation is low. Considering 2 times average, variation is high. So the case here about this table, the variation isn't that straightforward because we have not just one, we have 2 different basically percentage here. It's not just equal chance of having any of this basically group. So we have this thing called total variation distance. It's not complicated. Basically, it's you divided the eligible basically percentage of the eligibility here in this particular example minus the percentage of the panel, that the people that we had actually in the panel. So you get like this. Remember, this is the table. So this is not going to help because if we sum them up, we're going to get 0. So we need basically the absolute value. Okay, then we're summing them and we're dividing by 2. So basically this 0.18 is the total variation distance for this table, for this selection. So we're going to later use, let's run this thing. We're going to later use this variable and see how likely we get this distribution if we select randomly 100 people. So let's do the simulation. So what we're doing here, we're taking 10 random samples, right? You already know this sample. So I get black, black, other, black, other, black, other, black. So what's happening here? What I'm trying to do and what's going wrong? What's happening here? What is wrong here? Any comment? Any idea? Yeah, someone.
So panel and it doesn't change. Like it's always the same.
So basically, what I'm doing here, I have this table, right? I have this Swain table, and I'm taking 10 random samples. But it's not going to help me because I'm just taking like black, black, other. But actually, the actual chance shouldn't be equal, right? Because I have the higher chance of taking other than black, but this is not reflected here. So if this is my ethnicity, okay. I put the ethnicity, another table. I selected the column 0. This is my ethnicity. So I take, let's say, 20 samples from here. Okay, so these are my sample. But if I, for example, take 100 samples, okay, I'm taking from the ethnicity table 100 samples. And then I'm grouping them by the ethnicity. So I get black 55, other 45. If I run it again, I get 55 black. If I run it again, I get equal. If I run it again, equal. So you can see, basically, if I do this, the chance I'm taking, basically I'm giving each column, each row, 50% chance, right? If I run it 1,000 times, you can see it's almost equal, okay? So we are not going to do that because that's not what we need to do. We're going to basically we're going to select from others with 74% chance, from black with 26% chance. So this is the chance, right? This is I'm getting from this strain table, the column eligible. This is my array from the chance. So I call it population distribution. So we didn't see this one before, so this is new. So we are going to take here the sample, 10 sample, but we're going to consider this as our, basically the weight. Because these two columns, these two rows, they don't have the same weight. The black and other shouldn't have the same weight. This is 74%, this is 26%. Is it clear?
Yeah.
So we have this weight, we give them different weight. So now my samples, if I take the samples, you can see there are more others than black. In this one, no, but if I take one, you can see usually there should be more others than black. For example, here I have 8 others, 2 black, because they have different weight. So if I run it 100 times, you can see I get 81 other and 19 black. Is it clear so far? Questions? So we're selecting by that weight. So let's do that basically in that particular example. Let me. So what I'm doing here, I'm doing that. I'm putting in this table my selection again. But I'm taking the random. Okay, I'm taking random samples. So if I run, you can see I'm getting different values. How many of them are others? How many of them are black? Okay. So what I can do, something is here, I can just keep running this and see when I'm going to see 8% black and 92% others. I can keep running it, I can keep running it. But you can see it doesn't go really low. It doesn't even goes below 10. The lowest one so far we saw was 18. Okay. So, but another thing we can do is we can do basically put it basically defining it functions and running it multiple times to make sure to see when we get that that particular distribution. Okay, it's clear. Yes. So here I'm defining basically the table. We are having this black and others. This is the eligible among the population. Basically, 26% of the population are black, 74% are others. Among my panel, I had 8% of black and 92% of others. And this is my random selection. Okay, I'm selecting random, I get this value. I do another selection from people, I get this. I do another selection, I get this. So let's run that multiple times. So we just get this. We have these functions here. So we want to run that, for example, in this example, 1,000 times. We want to do that 1,000 times and see if by any chance we can get 8 out of 100. So if we run this, we get this. Okay. So I'm putting this result in this table. The table's name is result. I name it like this. So basically, it's a for loop running 1,000 times, okay, and calling my random jury basically panels, this one, okay. So I run, and here what I'm putting here is the TVD that is total variance, where is it? Total variation distance among my selection, between my selection and basically my selection, the random selection, and the eligibility. Okay, is it clear? Okay, I think not, but I don't see you're so convinced what's happening here, but you're shaking it. It's fine. I mean, don't get confused by the codes. The code is not important here. The thing that is important is what you're trying to do. I'm taking samples from my 100 people by that weight that I already defined. I'm taking 100%, and then I'm calculating the total variation distance. It means my samples minus the actual value in the society. Basically, this minus this. That's it. So I'm doing that 1,000 times, and I get these total random samples. If we do the histogram,
I have a question.
Yes.
And why do we need to do that?
So because we want, the point is we want to see how likely is this happens, you know. If I so okay, the idea is doesn't matter. The idea is I want to see how likely is I get 8 out of 100%. So the whole idea is here. This was the real case. This was the real case happen, and they mentioned no, this is pretty normal. By picking 100 random, you may have 8% of them black and 92 white. So I said, okay, let's try it. Let's try that and see how likely is it. So I'm doing that 1,000 times to see how likely is that. Okay. So in order to see how likely is that, I calculated this total variation distance. Total variation distance that I get this. This is the total variation distance between the real jury that they ruled and the society. This is total variation distance between my samples, my selections, and the society. And if I do it 1,000 times, then I'm doing the histogram. So you can see most of them are falling around here, 0.025 or 0.020 around this part. So you can see that was 0.8, right? The strain table, if you see, if we calculate the total variation distance, that was the actual what's happened. But I did 1,000 times samples. I took 1,000 times a sample from my society, and I never get even this close. You see, the lowest one is 0.17. You got what's happening? So I want to ask the question again. Is the actual jury panel likely?
No.
One of you said yes, it's possible. I want to see if he changed already his mind or is it still?
Oh yeah, it's totally possible, but it's very, very unlikely that it happened.
Very, very unlikely. I mean, when something gets super unlikely, like 0.001, it's really near unlikely. So, but the thing is, for example, you say, I mean, we're talking about the random selection. Okay, I mentioned random selection is not that easy or straightforward as you may think. For example, you say, I don't know, I go to the street and I pick from that particular county, I take 100 people from the street yeah, there might be 100 white people. Maybe you are, I don't know, near a Trump rally that they're all 100 and the rally is finished, they're all coming out and you're picking the samples and they're all white, of course. But that's not, you're not doing the selection correctly, okay? That's not their total random selections. So what we did here is totally random. We had the weight, you put the weight and you see the jury is literally unlikely. I don't know if I increase that 10,000 is going to change something. No, you get the same things. You get the, oh, sorry, I have to run this. Oops, it's running still. So what, okay, let's run. But what we see, it's very unlikely. So basically that jury was not fair. You can see I did that 10,000 times. I took samples from my county. It's literally impossible to have 8 out of 100. So that's all from today's course. Any comments so far?
No.
All clear?
All clear, teacher.
Okay. Yes. Okay, perfect. So I want to share you something very quickly. It's totally out of the topic, but it might help you with your life, with your study. Anyone of you heard the law of broken couch?
No.
No. Nope.
Anyone?
No.
No?
No.
Okay, you never heard of it because I just made it up. Okay, it's not a thing. I just totally made it up. But let's talk about an example. Okay, let's say there are two friends. Okay, going to, I don't know, to Home Depot and they buy a couch. And they come up, they try to assemble the couch, they put everything together, but there are like 1-2 pieces is missing from the couch. But they say it's fine. I mean, the couch is working. You can see it. You can use it. It's functioning. Okay. So they start using it without any problem. They work on it. But after a few days, couch start folding from the center. It's still doable. It's still seatable. A little bit uncomfortable, but it's still usable. So they just keep using it. They don't mind. It's still functioning. So after a few more days, the couch falls like, I don't know, more. They cannot even sit on it. They just hit each other when they sit on it. It becomes totally uncomfortable till it's finally get broken. So it's we can extend this, okay, to basically what we learn, okay, about in our studies, in our basically in your university courses. For example, you might be feeling very much comfortable in your, I don't know, linear algebra. You might feel you're doing everything good, great. There's no problem. You cannot solve. You're doing fine. But there are some 2-3 concepts that you didn't understand well, but it still doesn't cause you very much trouble. But when you go, for example, to nonlinear equation, then you might find, oh, I'm totally lost. I don't get anything. I don't understand any of this. What's happening here? I already reached my limits in understanding mathematics. But that's basically not true. We don't have the limits. What is missing is that 2-3 important pieces that you didn't take seriously when you were learning, because it didn't cause problem for you in those first stage. Okay, but continuing that later on, it make you problems, and then you feel that you got to your expiration date, you don't understand anything anymore. But basically, it's not true. So I mentioned math here. You just put it like programming here. For example, the thing that you're talking about, for example, you didn't really get how to work with random sampling here. For example, the weighted things, maybe you didn't totally understand, but okay, it's fine for now. But later on, it might cause problem. And not just this example, anything that you're supposed to know, but you didn't get it completely, but you just ignore and skip it. So that's the law of broken couch that we just made it up. It's basically it's shaky understanding make future concepts hard to understand. Okay. So like the couch, eventually your couch collapse or your understanding of that particular problem will collapse. So what you can do to address this problem is to do self-reflections and see what you're exactly learning, what you have a problem with, you didn't get it completely, you're struggling with. So you do articulate on your learning, try to find exactly those things that you haven't totally understood. Okay, and when you find out those missing pieces, then try to get help. Now there are tons of resources out there in the internet, YouTube. I mean, you're not going to have any problem, not just those, then your professors, including me. So try to get help for those broken pieces, okay? Don't just ignore them, because it's going to cause you problem at some point. So yeah, think about it. Try to think what's basically the missing pieces in your knowledge, and try to articulate on them and find solution and ask for help. That's it from today's course. But before we finishing, I want to tell you about the homework. We have an unusual homework this week. If you go to your basically Jupyter, you can see this folder in the shared folder. The name is COVID-19. So what I want you to do is basically, again, download it in your homework folder, check it out. There is a basically deadline, there is an instruction how to do it. There is some basic codes there you can run, but it's not like the others that I provide you codes so you fill it up. But what I want you to do is try to find some sources of information. I already put some sources there, the GitHub link that you can get great CSV files from the latest data. Okay, so for example, this is coming from the same source. It gets the latest information here using the CSV from the GitHub that I mentioned. So you can see the latest one here. If I see it's like 11, 12, just 2 hours, 1 hour ago, it's updated. You can see the total cases. You can study by, I don't know, by countries. So you have the CSV there. I don't want you to come up with this. Okay, that's what you see on the screen. But I want you to get those CSVs and try to like play around with them and see what you can do by the things that we already learned in the class. If you feel to go beyond it, it's totally fine. You can feel free to go beyond and do some complex, crazy stuff there. But you're free. You're totally free. What we're going to do is we're going to talk about all the things that you did during the next class. So what you're going to do is you're going to work with your project member. Okay, so it's a group project. You do it in a group of 2. There was just one group of 3 that was exceptions. So do it on the group of 2, and later we see next week what you came up with. Okay, there are a lot of resources out there in the internet. For example, I find one that these Pythons that uses the same SCV for having, for example, this type of graph, that's this type of data that you can get. It's totally fine borrowing codes from other resources, but make sure you understand what's happening there, because we're going to talk about it next week. Any questions about the homework?
No.
It's clear. I mean, there is no format really. It can be anything. It can be line chart, scatter chart, pie chart, whatever you can do with the data, just playing around with those CSV that are available. And we talk about those next week. I already announced it in the basically in the assignment in the NetAcad. You can check it out. If you go, you have this COVID-19 with the deadline. Deadline is Tuesday, March 31st, midnight, because I want it to be finished before the class. So that's a deadline. And what else? The slides are available here. If you are not still part of the Remind, please join, because there you can stay in touch with me much easier. I'm going to announce things there much faster. So yeah, that's it. That's all. I'm going to pause the recording. Any questions?
Nope.
No.
Yes, you can post things on Remind. Of course, you can ask me questions on Remind. If you want to ask everyone else that what I recommend, definitely use it, utilize it, is going to collaboration. Okay, and making a topics there. Making a topic so everyone can discuss. It's like a forum. Yeah, no, not this one. The conference. What was that? Yeah, here, for example, you can make a new topics and everyone can come and comments and solve your problem. But you can also ask me directly in Remind, and I try to be as available as I can. And I'm usually available there. I get the notification on my phone. So what was the question?
So the point of the homework is to try to simulate the cases of the sickness, or just show?
Yeah, let me see where I had the idea is basically to, you have the CSV tables there, and there are in GitHub, there are tons. You can get the, for example, latest results and do some analysis. Not necessarily should be complicated, but I want you to just play around with the data and see what you can come up with, what analysis you can do. That's the idea. So what I'm thinking to do maybe for further classes, if these things keep going on for longer term, I want to basically you do some sentiment analysis. I might go that way to use Twitter feeds to do sentiment analysis to find out what's happening in Mexico and how people are thinking, reacting to this situation. But for this particular one, you just get the data. There are good resources. Like this is, I think, GitHub. This is the GitHub. You can go, you can see there are data, there are tons of data. These are the, for example, daily reports. If you go there, you can see all the days from the first day till the last days. There are tons of data there. So you can download them and play around with them and see what you can come up with your team member. Questions?
Seems fine.
Is it clear?
Yes. All
Sure?
clear.
Okay, perfect. So if there is no more questions, let me stop sharing. So recording is going on. So any more questions?
No, I
clear?
think all fine.
So,
Okay, perfect. So take care, guys. Take care of yourself, and we'll be in touch through the Remind. Till next week.
See you.
See you.
Okay, teacher. See you next week.
See you next week.
Bye.
Thank you, teacher.
Thanks.
Bye.
Bye.
Thanks.
Bye, teacher.